So, just a quick comment about Con, and so I'm kind of seeing a few more missing assignments than typical. So let me know how I can help you get through those. I updated the grade book. Maybe it was just a matter of me updating the grade book to remind you of stuff that's out there is not complete. But yeah, let me know. Coming in and just to get some quiet time in the classroom during the day is always an option. You can come into this classroom any time of the day and do that. If you just need a quiet place to hang out and crank out some stuff. So just kind of keep that in mind. Okay, so the notes for today, they were a little long. I apologize for that. They ran longer than I like to have them run. I don't think it's really not super complicated stuff, but it's just kind of stuff that you need to kind of stop and think about. So the takeaways from the notes, okay, again, I'm stressing this just about every day, right? We're recovering information. That's what the accumulation function is doing. We're recovering information about the actual function by looking at the rate of change, the accumulation of the rate of change. It is just like Unit 5, when we were given the derivative graph, because we know the rate of change is the derivative. In fact, on Monday, we're going to stop calling it the accumulation function and all that stuff. We're going to just call it the derivative. We're integrating the derivative. That's kind of the vocabulary we're going to land on starting next week for reasons that just make it more efficient to narrow down the ways we say these things. But anyway, so this is just like having the graph of the derivative and looking at those features. Right, looking at where the derivative's positive, where the derivative's negative, where the we know that's where the function is increasing and decreasing. Looking at where the derivative is 0, those are critical points. Looking at whether it's changing plus to minus, minus to plus, then we can get mins and x's. Any extrema on those on the derivative graph is a point of inflection. So so it's literally what we were doing in Unit 5. So it's a good reinforcer. If you're shaky on that from Unit 5, you get an opportunity to kind of solidify those sort of ideas. So the fact that the notation is changing, right? We used to just call it f prime of x, and then look at and then talk about the features of f of x. Now the notation is just looking at that definite integral, and with the accumulation function, the derivative right there is the integrand. As far as finding the values of those definite integrals, so finding the areas of the regions, at this point, we were really relying on either those areas being geometric, so we can use geometry, or we're really relying on those areas being given to us, like in example, which one is that? The top of page 18, where they physically give us the values of those regions, and then we can work with those values in the same way we just work with numbers. If I want 2 adjacent regions, I'm just going to add those values together. So it works, they are just basically numbers. So we have all those properties that we have with just our normal numbering system. I mentioned 3 already, I guess. Really, geometric regions are calculated just like you're back in geometry. Just the caveat that when we're talking about definite integrals, we're talking about a function, and that function can have a positive function value or a negative function value, and that's going to impact whether the answer is positive or negative, because that function value is the height of the rectangle going back to our approximations and our Riemann sums. The f of x is the height, and the dx is the width of that rectangle, quite literally. So just realize that when we are in the underneath the x-axis, we then have negative values. And I guess I already mentioned this one too. A little out of order today. Adjacent regions can just be added together, just like physically taping shapes together. So any questions about the takeaways? Okay. I don't want to take up too much time because I want to give you really a decent amount of work time today to go through the topic questions and then crank out some content for sure. So there we go. So how can we use our knowledge of derivatives and geometry to recover information about the function? We're using our techniques in chapter 5. Okay, we know that accumulation function is just the derivative, that accumulating, integrating the rate of change is just looking at the derivative graph. And then we're going to apply our properties, I guess I should have said our math properties or our algebra properties, number properties, and our any geometric formulas that we can come up with as well. Okay, so class activities, we're going to crank out the topic questions. You've been pretty good about getting into those topic questions and cranking those out. So keep up the good work. You've been doing well on that front. These topic questions should be relatively quick because they are literally just, looking at regions and determining whether they should be positive, negative, or looking at graphs and using that feature table that I copied again from Unit 5, but I put it in today's notes too. Okay, so I'm not going to talk anymore. You guys are going to go ahead and crank out some stuff. I'll be here in case people at home have questions, and obviously I'm going to be making the rounds here in class too to check notes, things of that nature. So if virtual students, if you could just throw your notes in WebEx, that would be super awesome. And then scream out when you got a question.